Jeez, I'm connecting. We're live. Gosh, I'm connecting the power to my computer because streaming takes quite some resources, and yeah, and it's surprising, but we need to take that into account. And we're working on this problem. And it's called minimum height trees. And LeetCode problem number 310. So let me go through the problem statement and then say what I'm kind of expecting, what I'm trying to accomplish. Yeah. Overall, with this problem today, the overall goal is to see if I can get any work acceptable solution, not the perfect one, but any acceptable solution. And because I've looked at this problem yesterday, and I didn't see a perfect solution yet. So yeah, so let's try to exercise that. But let's go through the problem first. So we have a tree, but it's an undirected tree. It's a graph. I mean, it's calling this a tree. I mean, they wrote when you see in these test cases, they're rotating this tree like all the ways. I'm still kind of it's undirected graph. Yeah, so I'm still kind of learning these undirected trees, or but yeah. So we have a tree in an undirected graph. So a tree is an undirected graph in which any two vertices are connected by exactly one path. Okay. In other words, any connected graph without simple cycles is a tree. Okay, so this is just like definition. Okay, what they say. Okay, a tree is an undirected graph. This is good generalization of a tree. I mean, naturally, in our world, all the trees have some direction. Unless it's, yeah, this is more like a spider web. This is more like what are they called? Mushroom net. But yeah, in life, I mean, it's one thing that in computer science, the trees grow from top to bottom. But now we're talking about trees that don't even have one direction. Well, okay. What do you call? Is this an abstraction? Is this some kind of, I guess, everything is an abstraction, but this is a, okay, a tree in space. So not grounded, not anchored. The root could be any node. Okay, let's continue. Okay, I'm just trying to visualize this. Given a tree of n nodes labeled, okay, and an array of edges with n minus 1 edges, where edges I indicates that there is an undirected edge between the two nodes. Okay, so edge, yes, connects the nodes. So we have some pieces connected pieces, yeah, which is between the two nodes, A and B in the tree. Okay, you can choose any node of the tree as the root. Wonderful, yeah, so that's where we are. This is a intergalactic space tree, yeah, where when you select a node X as the root, the result tree has height h. Okay, so we actually have a height for that tree. Among all possible rooted trees, okay, those with minimum height are called minimum height trees. Okay, that makes sense. Minimum height. But okay, there is a definition, height of the height. So of a rooted tree is the number of edges. Okay, we're counting edges on the longest downward path between the root and a leaf. Okay, I don't know what downward is in space. So it looks like they're just okay. Let's just shake down. let's hold the tree by its root. Let all the branches fall down, and then there will be downward. Then, yeah. So we take this web graph from space where there's no gravity. Take it to our gravity world. Hold that web by this specific root, and all the branches go down. Okay, now we have a downward path to the leaves, and the longest downward path between that root and a leaf. Okay, that makes sense. That's the height. And we need to return a list of those minimum height trees. We need to return their root labels, the values. Oh, the root labels, yeah. You can return the answer in any order. Bold. Well, that is a hint. Okay, so there are some topics, there are some hints. There's a hint. And by the way, why not look at the topics maybe and see if I'm actually familiar with those? That it's not something out of my toolbox, current toolbox. Or before we do that, why not we try to solve this with a brute force solution? Brute force solutions sometimes are so keep it simple, stupid paradigm. Oriented. I mean, it's so helpful. And then in this case, it looks like the brute force for a worst case scenario. And the brute force we're thinking about is to go over all of the nodes, and for each node, go depth first search. So go again through, traverse the entire tree again, and see this maximum length, and that way figure out this length, save that length, and then track the minimum one, and then get those nodes with the minimum one. But by the way, to do that, we will need a map of we will need an adjacency table. I guess that's the proper term. Yeah, add adjacency matrix or table. Yeah, so basically for each node, so node, we will need, or vertex V, we will need all a list of all the adjacent vertices, yeah, that are directly connected through one edge. So yeah, I mean, we can, by the way, we could use that because they're all labeled from 1 to n. So we can use a slice of slices for that. And for each one, yeah, we'll have not only the one adjacency, but for each we'll have all the adjacencies. So good adjacency table will allow us to do to get that list in constant time. So some extra memory, but yeah. And so back to the brute force. For each node, we will do, which is a we can just do DFS traversal. Go traverse the entire graph, and for each node, traverse it again and get that length. So, and that sounds like n squared, and n in this problem is 10 to the power of 4 by multiplied by 2, so 20,000. And square of that should be 400. So it was 10 to the power of 4. Now it's 10 to the power of 8. So 400 million. That could be less than a second. Well, and in general, in our current world systems, computing time, and that could be within but it could be not. It might not be, but we can try, because because otherwise I'm pretty sure there is a linear solution here that will use probably some dynamic programming solution that will use, I mean, we can see pretty clearly that we can, for each node from the leaf, we can see that the path to the leaf is from a leaf, this upward direction is clearly determined, the length of the path. I mean, it's in that direction. So depending on which direction you're looking at, so that if you look at that branch as a branch for some tree, any of the nodes above, the downward or even downward, it doesn't matter, but directed towards that leaf basically. Yeah, so it will be one edge here, and then it will be a second edge here. So for this node, we know it takes one edge to get there. For this node, we know it takes one plus another, what was here plus one more. So we could be going from the leaves and going upstream. And in this case, we'll be going from it, since it's actually could be some kind of a web here. So we'll be going from the outer parameter to the middle. From each leaf, we'll be going, and we will know inwards. Yeah, we'll go inwards, and we'll know those. But at some point, we'll know those lengths. But at some point, we'll hit a situation where two branches merge and are connected to one node. So in that case, we will probably pick the longer one, I guess. So that's probably the logic to do that. So, and that one will continue. That one also can go from here. We can also go to other nodes, and their length will be that longest one plus that one. Yeah. So I feel like we're pretty close to a linear time complexity. A linear, time complexity solution. Yeah, I'm really tempted to do that. Really tempted. And it also feels like if I separate these subproblems, so we have already separated one, so adjacency table, which allows us to do DFS in linear time, traverse that tree. To traverse that tree in linear time, if we do this, start from the leaves and go inwards, if we do this breadth first search, how about that? If we start from leaves, save a longer path to leave. But where I was stuck with that was, and I think I'm again going to go in on the search for this linear solution instead of doing brute force. So where I was stuck with that was, so we like this node 3 will have a length, longest length. If we start from these leaves, it will get a longest length of 1, but it's not the final. So it's not the final value. That branch will bring it another length. So what I mean is, we'll have this conditional visited status. Status will be okay. We have updated, but it's not complete. not all of its sub-branches have submitted their length. And what by submitted we mean like this has been calculated. So, and but once we do have that, we don't have to go anymore. So that's kind of the end of the of the yeah, and we will track those lengths. So in our so we need another table with those lengths, basically. Yeah. Mm. Mm-hmm. And that means so each node will have its height, which is the longest downward path. Will be so that will be in the well, that suggests we need to revisit the nodes. That's what I mean. I'm a little bit, it's kind of the unusual approach. Not something I don't remember have been, because you might end up visiting that node as many times as as many edges it has. Yeah, because you might get there with one edge. So that edge will, or you might not enter. What you might also do is not enter its, not specify any length, any path, any length, until that node has all of its edges ready. Oh, how about that? Yeah, so we come to 3, and I mean we see 3, but so we'll have 4 leaves here, and these leaves will all try to update the length for this node 3, but they will see, okay, this node doesn't have, so it has from 1, it has from 1, it has from 2, we can get that, but it doesn't have from 4. So yeah, so let's not go there. So we'll get all the leaves in that case, and this 4 will also be not ready, right? And we'll be done with the leaves. Yeah, and there will be two inner nodes. They'll be like, okay, I don't know it's for 3, the value for 3. 4 will go like, yeah. So we might be stuck there. Yeah, we'll know the leaves, but we will not know these. So it looks like we will need, once we're done with the leaves, we'll need to visit 3, okay? Check currently available values on the 3. Say that 3 has this length, but it's, not final. Why it's not final? Yeah, we haven't updated the final length. So, but 3 will have something. We'll have 1 edge of a length. So 0, yeah, okay, once. It looks like a breadth first, but going inwards. And I do get a feeling that this problem might use some already established algorithm, like that I'm just trying to reinvent now. So reinventing the wheel a little bit. Yeah, we're looking at a wheel and reinventing it. Sort of a wheel. Yeah, but what that suggests, if is not a linear solution, that suggests n nodes multiplied by the number of edges. Yeah, so for each node, yeah, we'll visit 3, 1 for this length. Then yeah, 4 will also get something, and some suggestion, some partial data. Okay. Which basically is shorter branches. Okay, it's not their longest path, so you'll be getting shorter branches, but you have something. And but they will be longest branches so far, longest path so far. And then going breadth first inwards, we will get to these nodes, which have some preliminary data, and we'll see if we can update them. So we'll go around them and see if we can update them. We'll have a queue of these now. So this will be 3 and 4. And now they will have a little bit more information, but yeah, some might have, some longer paths. There might still not be connected, and some of them might not get anything. And that's kind of what I'm concerned. What if we have a situation where, so we got the information from the leaves, from these leaves, and this one has, but if there's like 1,000 more intermediaries between them, so that will but I mean, basically it will be the same thing. Yeah, we'll have this preliminary data, and so in this case we'll go through 4 and 3, and 4 will see a longer path and update itself, and 3 will see a longer path and update itself, and we'll have the answer. If there was and by the way, in that case, how many times did we visit 3 and 4? When we were visiting leaves, each leaf, each of these put on the next queue, the next row, and with the length. And by the way, well, actually not in the length. The fact that it puts something on the next queue means that it has some length to offer. And when we will be dealing with that node, we'll get through whatever is available through its edges, and we'll get the longest of them, and we just need to the longest of them. But let's say we start with 3, so now 3 has also the longest path. 4, and then we go to 4. 4 doesn't have it yet. So in this case, 4 will see also longer path. But we need to return to 3 after that as well. So yeah, 4 will see, okay, like 4 goes like, yeah, I have now the longest path, because it's final because I know it's from all the branches, all my edges. But the thing is that 3 will need to get on the queue again, because it did not have the final length. It will be waiting something from 4. Yeah, so we'll go through 3's. Visit 3 2 times in that case. I feel like we're pretty close to a more optimal solution. I'm not sure if it's completely linear. It's looks so we've been on 30 minutes on this session. And what if we try to implement that? So we'll have a queue, but you see, yeah, we'll need to revisit them. If 3, so we have some preliminary data for 3, but we see that 3 is not done yet. We need to put it on the queue again, basically. And on that queue, there will be all the nodes that don't yet have that full information. So there will be we'll be basically looping through them through the nodes until they all get full lengths. I wonder what the complexity of that would be, what the time complexity. Because let's say it's, yeah, if we imagine like, if you imagine a, in spider web, but it's not really spider web. I mean, spider web has a lot of connections. In this case, it's a, what do you call it? Snowflake, yeah. Snowflake with branches. And we start with the leaves, with the outer ones. And if there is like, let's say, a dozen of layers, then this one layer from the leaves, well, when we'll be going through that, so we'll know, and let's just, I mean, they're kind of identical, so we can imagine them as so there will be this layer. Let's call them layer, the outer layer. So 5, 4, 3. So this is the outer layer. Yeah. So these are leaves. Leaves. And so, or actually, yeah. Let's do the other way, because so that's the path, the length of the path. Yeah. So 2, 5. So we know this one, but this one is not 2 yet. It's 2 from that side, but it's, and we'll go like, we'll do a circle around these on the layer 2, and we'll know, okay, the currently maximum, so the maximum length so far for them is to get through them to the edge is 2. To the leaf, yeah. So there is this edge, and there is another edge, yeah. So, and where we'll be done with 2, but we are not, yeah, and we'll be done with 2. None of the layer in the layer 2. We're just talking about symmetrical approach now. What if it's symmetrical like that? Yeah. Symmetrical situation, yeah. For simplicity. So 2, we'll know, okay, the length so far that I know of is 2 edges. And we have to go further. We're not done, so we'll do the same with the next layer. And we'll know that the distance is 3 edges. And so on until we get to the center of the galaxy, of our snowflake. And at that point, so this is, let's say 5 is the center. So 5 will finally get the final length. It's gonna be the shortest in this case. But 5 will have it. Now from 5 that has it, we will need to do that again and go over all those leaves. So now we'll be going backwards. So we'll go to, and so that's not final, but now we'll go and see, okay, 4, layer 4, has, in this case, yeah. So we'll go back to layer 4. And the question is that already everything? And yeah, let's just do this symmetrical. For a symmetrical snowflake, it looks like it's gonna be everything. Yeah, so these flakes will know, we'll have all the data, I'm assuming. Yeah, so it's parent and its children. Yeah, let's just take the simplest case. We have just, linked list going from the center of the same length, so it's all symmetrical. And we have doubly linked list. And basically, so we hit the center. Which is 5 from all the directions. Yeah, there is like some number of linked lists of branches. But now we'll be going from the center, and in that case, it's pretty easy to imagine that that for this node we'll have the parent and its child. Yeah, so we have both of them, and we know where we are. What's our length is, what's our longest path is. So we'll do another traversal outwards, and that is linear. That looks linear, yeah. That does look linear. So yeah, we'll have the preliminary, but then they will get the max to 5 to the center, and starting from 5, which will have the length of 1, 2, 3, 4. Now we'll be building again that we'll be growing. So 5 will say, okay, there is 4 edges to the shortest leaf. And now it goes back, okay, maybe it's I don't know how to do it. Yeah, so yeah, but basically, I mean, in English, I understand it. Now, yeah, how to implement that. We'll need to do this length so far, and we'll fill out this length so far. And we'll be queuing, and we'll some point. Yeah, let's stick to the symmetrical situation. It's just easier to deal with. So this one case, simple basic case of when we were counting that length. Now we're going back, and 5 and yeah, it was carrying so 5 was carrying length of 4, but now it goes like to 4 to those 4s again, and it will be saying, okay, and now that length is 5, 3, Now the length is 6. And 2 for those 2's. From 3's, 2's will discover that there is actually a longer path, which is 7. And those 2's will also talk to 1's and tell them, okay, there is actually 8 edges to that side of the galaxy or the snowflake. And so 1's will need to learn, because 1's know only the distance to 1, but from the edge of from one edge of which is 0 of the snowflake, but from the other end, and they're only parent relative in that case, or it will know, okay, there's actually 8, maximum is 8. And that's how we can do that. So we'll do the inward traversal, and when do we know? Then the question is, how do we know we can go outward again? And we need to queue up those outward nodes. Queue them up again. Because in the first stage, we need to get our initial length. And that will be updated in the next stage. And it's going to be different with non-symmetrical. So this was a symmetrical graph here, but this one is non-symmetrical. And in this case, the leaves will talk to their parent or their relative, direct relative, and they'll tell them, okay, there is one edge each. And so for this, in this case, there is no center of the snowflake. So both 3 and 4 will be queued, and 3 will have preliminary, then 4 will have preliminary. And once we're done with preliminaries, so everybody knows their preliminary data, I think, that's the moment we can go again, but outwards. Okay, so given the timing, with that timing, because we have like 48 minutes now already, I think it's a good analysis. I'm still, but with that timing, it looks like this algorithm. So there are 2 problems here. Okay. So I'm not sure. We are already we're approaching the 1 hour, which is more than like an interview. So an interview situation. And this is more for practice then. But even for practice, I've been working on a general policy for myself. How long do I want to spend before I look up the hints on a problem? How long do I want to spend on a problem? And it feels like, because yeah, there, I mean, you can add extra time for yourself to kind of learn the skill of solving the harder problems with learning how to do that without any hints. But it's still, there is, I mean, some things you don't wanna reinvent the wheel. And also, yeah, basically, and also with your time. So some things you should learn. uh, and one approach to that is to look at the solutions and see, okay, so there's BFS, people are doing BFS. Yeah, so mhm, mhm. Simple idea, pick a root candidate and keep changing it to the child with the max height. So I see BFS. Okay, one other question I wanna. So it looks like this could be, in terms of length of code, this could be, interview format. Oh no! Oh no! This doesn't look like. I mean, if we use that solution, it's not interview format. It's like a page of code. Yeah. Oh, this one is more like it. Yeah, this one is more like it. What is it called? BFS. Mm-hmm. 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 So I just saw this hint. And they say like to cut off the leaves one by one until there is less than two vertices. And those, okay, one by one until those vertices will be the root of the minimum height trees. Jeez. So there is two ideas here. There's that there might not be that many. Wait a second. So cut off the leaves one by one. Why does it say less than two vertices? Okay, so there's like, what do they mean, less than two? Yeah, so there is a linear. Wow, cutting off the leaves. What a wonderful metaphor. Yeah, and by the way, this guy, I know this guy, who is doing that. So I like that. Yeah. He's good. Um, the vertices left will be the roots. Yeah, so the list, this adjacency table, Yeah, adjacency list for each vertex. And we find all the leaves, yeah. And then we cut them until there is okay, I'm trying to understand it. Okay, basically, I gave up. I think we were pretty close but it looks like the solution here is does not require doing this outwards. It's enough to do this outward, yeah, going back again over them. So it looks like there's enough. It looks like it could be enough just to do this once, starting from the leaves. Yeah, that's where I was also. Start from the leaves, but the idea of cutting the leaves, I mean, geez, it's so nice. And I mean, we're approaching the hour, so we're gonna take a break soon. I think I like the. Let me see if I can understand that in this last 5 minutes. And since we already looked up some solution, let's look at the topics here. Okay, it's depth for breadth first graph, topological sort. Topological sort. I am aware of that concept. I need to review that because it could be the key here, the topo sort. Topo sort could be the key to understanding this one. Yeah, those leaves and then their leaves. So what's the hint? How many can a graph have at most? Geez, that's one of the things, yeah. How many minimum height trees can a graph have at most? I need some water. So this one has 2. This one is 1. Yeah, what happens if we add one more here? My goodness. Oh my goodness. So let's say there is a vertex 6 here. Then the shortest path will be 1, 2, 1, 2, and that will be from 6. Because right now the shortest path is 1, 2. Also, oh, by the way, no. So, but yeah, now it's 1, 2 because it's so the shortest height. Yeah, the shortest height is the longest path. So the shortest height. If we hold the 4 up, it will be 1, 2, and for 3 it's 1, 2. If we have a vertex 6, so these it will still be 1, 2, but 4 will become longer. So only 1. We'll get only one. Only one minimum MHT. Yeah, minimum height tree. If we add 6, we'll have only 1. If we have 6 and 7. it will be 3 and there will be 2. So it looks like we don't get more than, with this scenario, we don't get that more than 2. Once we have 3 with this structure, once we get 3, so it could be maximum 2, and that could suggest us something. Okay, less than 2 vertices until we get. Okay, so I think I will look at it again. I will try to implement it myself because it's not too long in this case, this implementation. So I could do that, but maybe, I'll do my homework on this one and also review the topo search. So I think that's good. Thank you for watching. We'll see you in the next video.